Hey guys, thank you for being here. It is day 3 of the conference, and this is a pretty good showing for day 3. I'm a morning after. I'm sure you guys had a fun night, so thanks for being here. Pretty excited. My name's Henry Sowell. I'm the Hortonworks Federal CIO. I work very closely with this gentleman, Michael Young. He's a senior solutions engineer for Hortonworks. And importantly, he runs the cloud SME for all of Hortonworks. So really great guy, really smart brain.
He's being a little generous there, folks.
You'll see for yourself. But there's a lot of great content today, and that we want to get through. We've got several slides to hit. So,
and just a quick plug: Marcus WAINEO is a partner in crime of ours. Also, a really smart guy. Wasn't able to make it out, but he did help me with some of this analysis. So, just hats off to his contributions as well.
Yeah. So, just a quick overview of what we're going to be covering today. I'll go through kind of why we did this, why we're here, overviewing on which tools we used, some of the choices that we made, the clusters, and what I think that is going to be really significant for you is the results of the testing that we did, and the analysis that went into those results, and then we're going to also talk about what we're going to do in the future after this. So, why did we go through this process? As we go and look across the government space that we're in charge of, but then looking at what we're seeing in the commercial space as well, there's a huge move to the cloud, and there is a constant request to say, okay, we're getting ready to deploy. What instance types should we be using? And a lot of there are white papers out there. There are things that people have released, but they don't have a lot of the content and the drivers behind why those recommendations. If you talk to fellow engineers, it's usually anecdotal, and it'll say, hey, at this site we did and we used this, and it seemed to work. And that's not good enough for us. And what we really wanted to do was do some thorough testing to say, based on different workloads, based on, different instance types, what is going to match your needs for going to the cloud and do it in the most cost-effective manner. So we did that. We made some choices on the types of, in the test suite, the queries that we're running. You're going to see that it's not the full set of TPC-DS queries. We limited it to the longest running queries because performance results on something that finishes like that is not really getting what we wanted out of this. And then we did a cost analysis of each cluster configuration running these queries on the different workload types. And with that, I'll pass it over to Michael.
All right. How many of you guys are actively on AWS, Azure, or Google? Show of hand, please. All right. So no surprise, a lot of people are out there. How many are not yet out there but are looking to migrate to the cloud in some way? All right, so a very large percentage of the population in the room. And that is the reason that we did these benchmarks. I spent, probably 3 weeks running lots and lots of benchmarks. And the point is so that we could provide, numbers-based, actual database recommendations to customers, to the community. The idea is often, well, I'm just going to use this really fast server. It's more expensive, but it's fast, and the queries are super fast. But if you actually start looking at price and performance, what you'll realize is that the most expensive server and theoretically the fastest server doesn't yield the best overall performance specific to a Hadoop type of workload. So given that, what we wanted to do was use industry standard benchmarks. So these should be benchmarks you guys are familiar with. When you're looking at a Hive-based workload, TPC-DS is pretty much the standard for determining what the relative performance of Hive is in different configurations and different data sizes. What we chose to do was do 5 runs of TPC-DS. That's why I also spent 3 weeks benchmarking. It takes a while to run through all that. And then we averaged it, right? So every query was run 5 times sequentially to get the average. Part of that was just to make sure that we're accounting for variance of hotspotting within a particular, particular cluster build that you might not see, in another cluster build. Also to account for variance in storage, because in the cloud you get a lot of variance. You might have really good solid throughput, but it tends to spike up and down quite a bit. So we ran 5 of those. We tested the 50 gig and 100 gig data sets, and why is that? You'll see a lot of benchmarks when organizations, and we'll do this as well, we'll say, hey, we're going to test against 1 terabyte of data, and that's great. That really is a sort of a big data use case, but a lot of customers who are just going to the cloud, they're not necessarily dealing yet with that size of data. They're looking at much smaller data. So what we wanted to show was, here's 50 gigs of data. This is a getting started kind of configuration, and then we wanted to double that data size to see if the performance differential was consistent, right? Or if there was some significant change that was really surprising for us. Test DFS IO, again, that's an industry standard benchmark for Hadoop-based IO. It is not normally representative of a lot of Hadoop workloads. What it's really intended to do is give you a solid baseline that the disk IO performance of your clusters is meeting anticipated levels. What we'll show here is that while Test DFS IO looks phenomenal for some servers, it didn't actually result in better overall Hadoop workload performance. And so that was that was an interesting takeaway, and we'll show you that. And then Terasort and TeraGen, also part of that is TeraValidate. I did not run the TeraValidate, just tons of benchmarks and ran out of time. Terasort really is the one that's a heavy lift, and that's representative of a traditional MapReduce workload. So the idea here, what are the 2 common workloads that you traditionally see with Hadoop? It's Hive and it's MapReduce. The third one is Spark. We did not have an opportunity to test that. We'll talk about future where we've got lots of plans to try to put out some community direction here. So cluster configurations. Typically what customers do when they look at the cloud is their first thought is almost always lift and shift. I've got this configuration on-prem, I'm just going to run that in the cloud. And that's okay from a starting point, just, this is what I'm comfortable with, but it's one of those sort of things where the next step is, can I save money, right? Can I optimize this in a more efficient way? So what we typically recommend at Hortonworks is a minimum of 12 to 16 nodes for a production quality cluster, particularly on-prem. So what we wanted to do was represent a cluster that we see very commonly in new customers, new deployments, on-prem. And so that's 3 master nodes, that's 1 client node, and 10 slave nodes. All of these performance benchmarks were done in the US East 1A availability zone. The reason for that is we didn't want to have any variances in potential zones and or regions causing performance differentials. Having said that, from one cluster build to the next, there was quite a bit of variance just in terms of some clusters, running 5 TPCS queries. It's like, oh wow, that one had 2 spikes that the other one didn't have. And maybe it was the time of day. So we tried to control as many variables as we can, but at the end of the day, there are some that you just can't completely control. So we did test a very specific set of instance configurations. The reason why are these are commonly communicated to us from professional services, customers who are like, hey, I'm thinking about using this combination. So we tested the M4, both extra large and 4 extra large. The M5s, which are relatively new, they were announced last year, I think in November of last year. And then because you're in the cloud, you start to see a lot of people asking about, breaking up, separating compute from storage. And so the last 2 configurations are some pretty commonly asked about configurations where you use really optimized storage for data nodes, and then you use some pretty beefy compute nodes. So there'll be some pretty interesting results there in terms of what those look like. Any questions on that so far? So how do we do this? All clusters, a plug for a product that I love very much. It's called Cloudbreak. 2.4.1 is what I use for this. When I'm building, 8 different cluster configurations and I'm doing it with 3 different storage types and I'm doing it over weeks, I don't want to build these clusters by hand. So I use Cloudbreak to have a very consistent deployment experience. I used the Cloudbreak CLI to execute the cluster build command using a JSON file. It literally took me 5 seconds to get the cluster started, right? And then I'm just waiting for Amazon to kick off, and then I go off and run my benchmark. So Cloudbreak is there. We were using HTTP 2.6.1.3, which is the default in Cloudbreak 2.4.1, and this is based on HTTP 2.6.4. Again, the idea behind theirs was also to make it reproducible. So I do have a GitHub repo that documents the steps that I went through for creating these clusters, the JSON files that you can actually use to run this on your own instance types. And then, to try to do an apples to apples as much as possible for your particular workloads using the same kind of baseline configurations. One of the things I want to point out is that We use the basic blueprint that ships out of the box with Cloudbreak, right? The idea there is that's what a lot of people are going to do. They're not necessarily going to go in and then immediately start tuning their cluster. One of those reasons is it's hard to tune clusters, and they don't always know all of the buttons to push and the knobs to turn. So what we wanted to do was say, hey, look, just out of the box, if you don't do anything else, this is the kind of relative performance that you're going to see. And we'll show you where there is room for some performance tuning. So just to give you an idea, this is the cluster layout. I don't know if you guys can see that okay, but when we built the 10 data node version of the clusters, this is the blueprint from Cloudbreak. And just to make sure everyone understands, Cloudbreak is actually using an Ambari blueprint. So this isn't in any kind of way proprietary. It's just using standard cluster configurations. Then we actually I made a blueprint for compute because the last two configurations we tested was a compute with separated data storage. So in terms of what that looks like, right? So once I have a cluster up and running, this is the Cloudbreak interface that's showing you, where it's deployed. It's out on Amazon, how many nodes I have, right? I've got easy access to direct links out to AWS so I can tweak any security group settings that I needed to. Gives me uptime and IP addresses. So, again, it was super easy to see kind of what was going on with the cluster. So first set of results. The first thing we wanted to do was look at disk I/O, right? We wanted to say, okay, some of these instances, the i3s have NVMe, right? It's crazy fast. So first thing I said, I'm going to test that first. I want to see the magic, right? I want to see what that can do. So I go ahead and I ran the tests of DFS-IO. Again, we did 50 gig and 100 gig, not because we thought 100 gig would necessarily yield any different performance. It was just to make sure, just to check the box and make sure we're not missing something there. So these are the commands that we ran. First thing we do is we write out a bunch of files and then you read a bunch of files. Pretty standard, but just so everyone knows, these are the commands that we ran. Now for what you all came for. All right, so this is the write performance of 50 gig data size. So the thing that I want to call out for you here is that higher is better. May not necessarily be obvious, right? I've got the little plug there, but it's hard to see. Can anybody guess, if you can actually read it, yellow? Which one was that? That was the NVMe, right? Incredibly fast performance by the NVMe system. I was like, all right, that's what I expected. This is going to be some good stuff, all right? I'm like, this is good stuff. You'll notice that there's a lot of variance here. You see the spikes there on the yellow and kind of, or not the yellow, the orange and kind of brownish there, right? What was interesting about that is I also, I tested M4 and M5. That's the M5. Why is the M5 instance so much faster using EBS? The same EBS that I attached to the M4. Well, the reality is the new M5 instances actually have some really phenomenal peak bandwidth potential, but there's a caveat, right? So if you go out to AWS website, you'll look, and the caveat is that it can achieve that like in the first 30 minutes of a 24-hour period, right? So what happens is you can get really good performance, like beyond average, but then it drops off, right? So just keep that in mind. If you go out to the EBS website for Amazon, you'll see that they do have a caveat. Hey, it's got great performance potential, but we only guarantee a 30-minute window where that's going to happen. Having said that, its baseline performance is still on average 14% better than the M4s. So I didn't have a whole lot of surprises here. I expected NVMe to be crazy fast. I did not expect the M5 to show up there quite as fast as it did. The thing that did surprise me is that D2 instance, right? D2 is it's a storage dense node. It's designed kind of for those. I have a lot of data that I need to store, and I want to do it cost effectively. But the performance was lagging there quite a bit, and I was really, really surprised by that. So one of the things I'll point out here is that when you go to the read side, right? So the read side is a little bit different. You'll notice that those M5s, they're not spiking the same way they did on the right side. But NVMe, really good on writes. No surprise there, just like it is on reads. But the D2s perform a little bit better. Now, why is that important? When you're talking about Hadoop workloads, you're doing a lot of reads, right? There's a lot of reads in traditional Hadoop workloads. So on the read side of things, the D2, they're looking pretty good. So I wasn't too incredibly surprised by this. So I went ahead and I ran the 100 gig. Now, I will throw out a caveat here. I didn't have time to test the M5s at the 100 gig size, but I tried to do a one-for-one between each of the sizes, at least on the M4s, to show you, a performance comparison. And again, at 100 gigs, no surprise, you see that, that the NVMe is leading the pack. And then, but interestingly enough, look at that D2. Why is it so low? When I ran it on the 50 gig side of things, right, when I ran that test, it was actually pretty compelling on a read, but we're not seeing that here. This points to that variance that we're seeing on the EBS performance, right? It's not that 100 gigs is necessarily a worse set of data that the node has to handle. It really is that there was just a lot of variance in terms of what EBS was doing on those volumes. So I took this and I said, okay, now I've got an idea. I'm expecting that i3 configuration, that thing's going to scream. This is going to be some good stuff, and I'm going to go and I'm going to tell customers and other people in the community, use that i3. And then I ran TPCDS. Right, so the idea behind TPCDS is, Hive is the data warehouse for Hadoop. And many customers, they're using SQL, therefore they're using Hive. So what we wanted to do was we wanted to demonstrate what an actual workload's going to look like on the cluster for your average customer. So like I said, I do have a repo out there. You can go out there, you can see the steps that I went through, all the commands that I ran. And my version of my repo has just those 9 queries. I basically took a subset of the original Hive test bench that Hortonworks has a repo around. So pretty simple process. You run a build. You actually only have to do that once. You don't need to do it every time. But you do need to do a setup for each of the data sizes that you're going to use, because it goes out and it creates a bunch of tables. It's like 24 different tables, I think, that it creates. So I went ahead and I ran that. Any surprises here? So, lower is better. Shorter bars are better. I want to draw your attention consistently to the blue and the green there that seems to be lower. That's not the D2, and it's not the i3, just from a performance perspective, right? That's what you're looking at there are the M5, right, 4 extra large, and the M5 4 extra large SSD. So one of the other factors was to consider SSD attached storage versus magnetic storage versus the throughput optimized magnetic storage. So one of the things you'll see is that those i3s and the D2s, while they are better than the extra large version, right, they are nowhere near as competitive as the M5s, right? So the M5 really shines here. The other thing you'll notice is that the SSD performance of those M5s, right, it looks pretty good, but take a look at this orange one here, M4 extra large ST1, that's throughput optimized. What you'll see is that the throughput optimized hard drives, no surprise, because if you go out to the EBS website for Amazon, they'll tell you, right, it'll say, hey, look, this is really optimized for like big data workloads and data warehouse workloads. So I'm not completely surprised, but spinning disk is competitive, right? It's competitive with those GP2 SSDs. So the takeaway here is that the 50 gig size, those M5 4 extra large are crazy good, and they're much better than the distributed compute storage using the i3s with NVMe. So the takeaway is, one, that the M5 4 extra large are really good from a performance perspective, but two, the other takeaway is that the performance of test DFSIO, the actual disk throughput performance, did not translate into a corresponding Hive relative performance, right? Not surprising, right? Because Hive is not necessarily very heavy on writes, right? There obviously are reads going on, but a lot of it is, loading up the data and it's doing the computation. So there's a lot of computation involved there. But I was really surprised. I really thought that the i3s would just be a lot more competitive than they are. So if we move on to the 100 gigabyte size, you'll notice that the chart looks very similar. And the point of this is to show we doubled the data size. And we didn't see that the bigger instances somehow, jumped because they had more capability. In the R3 configuration, or when you look at the compute and memory, even though there were only 6 compute nodes in that configuration, they had more compute and more memory than the 10 data node configuration. So it's not a lack of resources. And clearly the I/O speed of those 4 data nodes, they should have been able to make up for the fact that there's only 4 of those instead of 10 across the board. But we're not seeing that in actual translation. So the takeaway here is M5 4 extra large, great performance, right? SSD is good, but what we're seeing, at least on the 4 extra large, the ST1 performance was very compelling. All right, so Terasort and Teragen. Again, this is the MapReduce workload. So a lot of people are still doing, MapReduce style, queries. They're running, their custom analytics and things like that. So these are standard commands you can go run. This is an example of how you do that. Tested both the 50 and 100 gig, again, for consistency. So on the left is TeraGen, that's heavily right. On the right is Terasort, which is reading in all the data, doing a sort of it, and then writing it back out again. What do you notice here? With these instances, there's a lot less real differentiation in terms of overall throughput for Terasort, right, the MapReduce style, than Hive. Hive had a lot more variance, right? You really could see very clear differences, significant differences in performance for Hive that you just don't quite see with Terasort. So I'm like, well, wait a minute, let's go to the 100 gig and see what happens. Really no different, all right? We doubled the data size, but we see a very consistent performance. Now, in this case, the D2s and the i3 style instances, they were more competitive, right? They were, still slower, but closer in range. The next step, though, is to actually take a look at, the performance with the price as a major factor. Why? When you're going to the cloud, one of the things that you're looking to do is save money. So going out and grabbing the fastest instance type of whatever that may be is seldom the answer. It's the fastest instance type at the right price point that meets your SLAs. And we'll talk a little bit about that in terms of recommendation. But when you actually look at the price performance, this is where you're really starting to see, what instance type you should use. Lower is better. Right, so this is what it would cost. So what we did was took all the Hive queries we ran, and we just said, what was the average time it take to run any one of these Hive queries, right? And then we calculated what the cost was based on the instance type and based on the attached storage for the duration of that query, which is measured in seconds, right? So all of the price is typically per hour, right, for CPU instances. It is per month, associated with gigabytes per storage. We normalized all that down into seconds and said, okay, for this configuration, this job took 165 seconds, here's the cost. What you'll notice is, look at the price point for the i3s and the D2s, right? Crazy high. But their performance no way justifies spending that amount of price differential, right, in order to use those instance types. And again, while the performance of the M5 4 extra large and the M4 4 extra large were really good, when you factor in price, it's even better, right? It's very, very competitive there. So that's on a per query basis. Another thing customers will do is they'll say, great, I know what it might cost me per query. And if you look at the numbers here, it's actually in cents. It's not crazy expensive on a per query basis. But if my daily workload is something like TPCDS, I'm going to run 9 complex Hive queries, right? And I might do it 5 times for whatever reason. That's 45 total queries that are being run, right? What was the total execution time of that measured in seconds? What did it cost me to run that? So this here is just showing you the 100 gig. Again, no surprise, right? Charts look very similar. Increasing the data size did not have a significant impact. But when you look at the total cost, right, you'll notice now it's measured in dollars, right? It's no longer cents. Now it's measured in dollars because a lot of these running 9 queries 5 times, we're looking at anywhere between 6,000 and 7,000 seconds for some of these clusters. You'll see that the D2 and the i3 instance types, right, they're significantly more expensive in terms of dollars, and it just doesn't justify using those at all when you're running Hive queries, right? I mean, it's crazy, right? So focus here is the M5 4 extra large, phenomenal value, fantastic performance, right? I mean, why choose anything else? So again, same thing for the 100 gig, we doubled the size. The chart looks pretty similar. Again, for the 100 gig side, I didn't have an opportunity to test the M5 extra large. I expect it to fit in very similarly that it did to the 50 gig size here. But what's the next price performance? And that is MapReduce, right? So we did the TeraGen and the Terasort, and you'll notice some differences here. The differences is that while the M5 performance was overall best, the M4 the 4 extra large was overall best. The extra large, right, was still pretty competitive overall. When you factor in cost, you'll see that the M5 extra large, right, which is one of the smaller instances you can get, is actually very compelling for a MapReduce workload. So when you're thinking to yourself, oh, I'm just going to go buy the 4 extra large, or I'm going to use the 4 extra large for everything, you do need to consider your workload. You have to consider the kind of job you're running on that cluster, because it makes a difference. Well, one of the advantages of having something like Yarn in your system is that you could actually have a mix of clusters, right? A mix of instance types in your cluster. You could have M4 extra large with a queue dedicated to MapReduce style jobs. You can have M4 4 extra large with a queue dedicated to Hive-style queries. So you get the best of both worlds, right? You're getting the best overall performance combination you possibly can. And again, 100 gigs, no real surprise there. It's pretty consistent. So let's talk about some recommendations. I mentioned it a little bit earlier. You need to consider your workload type, right? Clearly, different workloads, right, have different requirements in terms of performance. And while you can go out and say, I'm just going to use the M5 4 extra large across the board, right? When in doubt, go ahead and do that. But prior to doing that, at least take into consideration, what is my workload type? Am I predominantly Hive? Am I predominantly MapReduce? Am I doing a mix of it, right? And then pick the appropriate instance type. Also consider performance SLAs. While the price to performance ratio of an M4 or an M5 extra large is very compelling to MapReduce, it doesn't matter if you're not meeting your SLAs, right? So while it might be a little slower, but it's crazily cost effective, you have to meet your SLAs. So first, consider your workload type. Second, consider your performance SLAs and make sure that your queries are finishing in the time you need them to finish in. So for Hive, without a doubt, we recommend the M5 4 extra large, right? Best overall performance, best price performance ratio, no question there. For the MapReduce yarn style workload, it's a little bit murkier, right? So the M5 extra large is clearly the cheapest, right? Price performance, but it's not necessarily the fastest. So that's where the whole performance SLA comes in. So the M5 extra large, it's competitive, right? So consider that as your go-to. But you may realize that with your performance SLAs, you do need faster queries, and that's where you start looking at that 4 extra large, right? And like I said, if your SLAs demand, use the 4 extra large. So let's talk about the D2s and the i3s really quick. The big thing there is they're crazy expensive, and I'm not saying that they're not useful instance types to have, but another caveat there is the storage on those is ephemeral, right? So what does that mean? Well, that means if I shut my cluster down to save money, I've lost my HDFS. It's now corrupt because my data has been wiped away. So if you're going to use D2s and you're going to use i3s, you need to use them appropriately. And how is that? Well, if the storage is ephemeral, perhaps they should be associated with ephemeral clusters, right? So as long as they're running, you're happy, and when you shut them down, you have no intention at all of keeping them. So I'm not saying don't use those instance type, but use them with caution, right? And most importantly, their performance, at least in the testing that I've done, right, with all the given caveats, just doesn't warrant spending all that extra money because you're just not getting the performance out of them you should. So use those with caution. So storage recommendations. And this is the thing that I was honest, this was the biggest takeaway I had in terms of just personal surprise. I really thought that the GP2 SSDs would be consistently faster all the time. What you'll see in the Hive benchmarks, particularly for like the M4 4 extra large, the ST1, the throughput optimized hard drive, was very competitive, right? It was, at most a couple of percentage slower than the SSD. Now, why does that matter? The ST1 instant or the ST1 storage type is a little bit less than half the cost of the SSD. So if you can get like 95% of the performance at half the cost, why wouldn't you do that? Right? And you tell yourself, okay, well, I looked at the numbers, right? So for running the Hive queries, right, it might cost me $12 for the instance. The storage probably cost me 4.5 cents total, right, for the seconds that it was running. Well, what do I care if I'm spending 2.5 cents? I'm at much smaller data sizes. When you get to a point where you might have terabytes of attached instance storage, that's when it matters because the costs do significantly increase. So it's smaller data sizes. The storage type might not matter to you too much. You can attach those GP2s, but as you start getting into the terabyte range, the cost of storage is going to become a bigger factor for you. And the ST1 is clearly performant, and it's half the cost. So why spend extra money if you don't have to? Now, having said that, that's targeted data nodes, right? The ST1s are really good at the workload that the data nodes are inherently doing. For your master servers, for your compute servers, and your client servers, those are all going to be better able to take advantage of the GP2 storage, right? Because it doesn't have the same access patterns, right? A master server is more like a traditional, web server where you do want, fast I/O, but it's not doing all of that, massive amounts of data reading and writing out on the cluster. So let's talk a little bit about what the metrics of the cluster look like. So what I wanted to show you here is an interesting point. All of the machines consistently, regardless of size, so no matter what instance types I had in my cluster, I was using between 50 and 60% of available CPU. What does that tell me? That tells me that there is plenty of CPU headroom on the cluster. Now, granted, tuning all of this stuff is fairly complex, but in order to get the best overall performance, you do want to actually try to use as much of the CPU as you can. So there clearly is an opportunity to do some tweaking of the cluster so that you're using a little bit more CPU, right? You don't want to necessarily hit 100% all the time, but you definitely want to use more than 50% of your cluster CPU capacity. And every chart, right, that I saw for all of the clusters, they were very consistent in the amount of CPU they were using. So there is an opportunity to do some performance testing and tuning here. But here's the thing. It doesn't really make sense to tune my cluster to get an optimal performance benchmark, right? That's not really helpful at all. Sure, it might tell you that I can achieve some great, fantastic outcome by running this benchmark, but the reality is that your real workloads, the workloads that you run every day, may not look anything like the performance benchmarks. So don't go tuning your cluster just to get the optimal TPCDS when your Hive queries are nowhere near as complex, right? And maybe you're not using as much data. So always tune your cluster specifically for your workloads, okay? That's the important takeaway. So while there was headroom for tuning this cluster, I would never recommend that you go and tune it just based on benchmark performance alone. Actually run queries, collect the data on your queries, right? And then make determinations based on that. If you guys are interested in learning a little bit more about like the pricing, so I've just got some quick links out here. You can also Google search it, but the last link there I think is the important one, talking about the EBS optimized volumes. I would point out that when the M5 instances were first announced, I think it was in November, initially Amazon said stay away from the ST1 storage type that I tested for the M4s. All right, there's performance issues, don't use those. I think in January of this year, they retracted that and said, hey, we've resolved the issue, it's okay, go ahead and use ST1. But you need to read the fine print. So if you go out there and you look at that, you'll find that sometimes Amazon will say, here's the maximum bandwidth, here's the maximum IOPS, and then there's an asterisk, right? And it's typically for the newer instance types. And you go look at the asterisk, and there often are caveats around what the advertised max throughput may be and what you can achieve at any given time. So just be cognizant. Don't just go look at some number in a chart, like I typically will do. And Marcus, my partner, was like, hey, did you see that caveat? Like, what caveat, right? So I was talking to our Cloud SME group, and I'm like, hey, have you guys seen that caveat? And they were like, oh, that's really good to know. Thanks for sharing that with us. So, always read the docs.
So, Michael. Here, can I borrow this for
Yeah, you can borrow that. Here, I'll take this one.
All right. Hey, that was really great. Thanks, Michael. As you guys have, throughout this whole conference, there's a couple things that have been coming out, and I'm sure you've been hearing. Make sure you choose the right use case for the cloud, but I think that we show here that also choose the right cloud instance type for your use case, which I think is really important. And when you look at scaling this up to your real world use case, there's actual major cost and performance impacts to choosing the right instance type. One of the things that we're doing as looking towards the future, we've been talking about multi-cloud. Who in here is doing stuff on Azure? Okay, Google Cloud? Okay, we've got a few. Well, I'm sure you probably want to know what this looks like on those clouds as well. So when we look at future testing, we're planning on doing this same type of testing on the other platforms as well. So look forward to those coming out. We should have more resources coming out from Hortonworks, blog posts, and some of these performance pieces. We'll get this presentation out as well. We also want to talk a little bit about beyond just the technologies that we're looking at today to some other technologies and testing that we're going to do as well.
Yeah. So while it's great to talk about Hive and it's great to talk about, MapReduce style workloads, there are customers who are Spark only. There are customers who heavily use HBase. There are people out there who are big Kafka users. So one of the things that we want to look at is to try to reproduce this style methodology, right, in the cloud for the various instance types across the cloud platforms and do the same baseline testing for Kafka, right? Do the same baseline testing for HBase to provide that, recommendation based on actual data, because the reality is that HBase workloads, they don't look like Hive workloads, right? Kafka workloads don't look like HBase workloads. They're different tools with different criteria in terms of what they're trying to do. So what we plan to do, and again, this all just takes time, right, is to test each of those major types of workloads, provide some data that's consistent across the cloud platforms and say, hey, if you have a Kafka use case and you're deploying on Google, here's our recommendation for the instance types, right? And similarly for like HBase and Spark. So look for future talks on the horizon, hopefully things on our website where we're going to be talking about some benchmarks that we've run on the other cloud platforms as well as using these other workload types.
All right, guys, we'd like to open it up to questions. I've got 3 hats for the first 3 people that ask a question. So if you would it's pretty exciting times. Huh? All right, here we go.
Okay, so you have a standard blueprint, certain number of nodes, certain number of cores, everything. What is your assessment of fewer cores, more nodes versus fewer nodes, more cores relative to this benchmark? Spreading the workload out across more servers to talk to the I/O.
So the question is, what is our assessment of using more nodes but fewer cores and perhaps memory per node, right? The answer to that is we had not yet tested that, other than the i3 and the R4 configuration. That is fewer nodes but with more overall CPUs. That's another tilt of that. The answer is that Hadoop is designed to scale horizontally, right? So in general, you will often see better performance by having more nodes, even if those nodes are smaller, right? That's not necessarily universal, but for the most part, that's what we see. Obviously, depending on the amount of data that you're having to move across the network, that could be an impact, right? Because as soon as you involve the network, things are going to be slower than they are local to those nodes. But for the most part, our belief is that having more smaller nodes will generally yield you better performance. There's a caveat to that, right? So as an example, Hive LLAP. LLAP is a capability that you can enable to get real-time interactive Hive queries. That caching daemon really works well with at least 16 gigs of memory. So if you go deploy a bunch of those and you turn on Hive LLAP and you've only got 8 gigs, it's not going to be good, right? So depending on your workload, as long as you're using a minimal configuration that has sufficient memory, I think that you will overall see better performance with more nodes.
Did you tested the data node encryption or exchange of data on the cloud?
Right. So the question is, did we test encryption of the data nodes, right? There are a lot of people out there who enable SSL, right? TLS between the nodes. The answer is I have not tested that, but I have seen performance benchmarks. Encryption, right, between nodes, particularly like data nodes, can have a 20 to 30% performance impact. Again, it depends on the encryption you're using. It depends on if you have hardware acceleration for that encryption. But there is absolutely a performance impact. I think you're probably looking at about 20% maybe on average as a good guide pole of what can I expect the performance impact to be. I did not test that in this particular round.
So did you have any comparison between if you run local with bare metal and the safer drive?
So that's a great question. If someone wants to donate servers for my basement, I would love to. No exaggeration. I was up till midnight, 3 weeks straight testing all this stuff in the cloud. I don't have access to physical hardware. I believe that there are a lot of benchmarks out there. You could take some existing benchmarks at TPCDS, say 1 terabyte level, and just run those queries in the cloud and say, okay, somebody published it, here was their configuration, right? Their configuration was this. I'm going to represent something similar in the cloud at the same data sizes, and you could get pretty close to doing that comparison. I just don't have the resources to do that local testing. It's a valid point, right? Because maybe you aren't necessarily going to the cloud and you're looking for similar recommendations. We have a lot of material around on-prem. The part that tends to be missing is the more cloud-specific version. Anybody else? That is a great question. So on Monday, I attended the NiFi meetup because NiFi's cool, right? NiFi's cool, everybody. I love NiFi, right? I use it every chance I get. And I was thinking to myself, how can I test NiFi, right? So I'm actually thinking about ways of using Cloudbreak, because Cloudbreak 2.7 supports deploying a NiFi cluster, by the way. I'm thinking of ways of having a reproducible, and that's the important part, it's got to be reproducible. Thinking of ways that I can generate a relatively common kind of flow, push data through, right, so that I can run that on different instance types. So I haven't done it yet, but I am thinking about ways of doing that. Would certainly love to have you guys reach out to me if you've got ideas. If you'd like to collaborate, let me know. All right, well that's.
All right, if you guys have anything, we're going to be standing up here or right outside.
Right outside.
Room. So.
Really appreciate you all coming out. Hopefully you found this helpful.